The James Webb Space Telescope, JWST, has been surprising us with new results that we can't yet explain for the past few years now. Everything from little red dot galaxies to the overmassive galaxies in the early universe, and finding galaxies with features like spiral arms earlier in the universe than we ever thought that they should exist. And this month was no exception, with this paper by Smethurst and collaborators from the Galaxy Zoo and Sears teams, which claims to have found featureless disc-shaped galaxies way earlier in the universe's history than we ever thought possible. That's right, in this video we're talking about my own research, and I'm so excited that it's finally been published so that we can just chat all about it. So in this video we're going to dive into what are featureless discs and why do we care about them, then how we found these featureless discs in JWST data thanks to the citizen science project Galaxy Zoo. Then we'll chat about whether the things that we found truly are featureless discs or just look that way thanks to how far away they are. And then finally, what this means for how galaxies evolve in the universe. And if you love deep dives like this into the big unknowns in science, then you've got to check out Nautilus, who are the sponsor of this week's video. Nautilus likes to cover ideas that will be debated long into the future, which is why Nautilus has established itself as the foremost literary science magazine, and also my personal favourite science magazine as well. Some of the most well-regarded scientific minds in the world read and write for Nautilus, including literary giants like the late Cormac McCarthy, who published the only non-fiction piece of his career in Nautilus, or senior scientist for astrobiology at NASA Ames Research Centre, Caleb Scharf, who regularly contributes reflections on our place in the universe. Which is why I know that all of you will particularly enjoy its Cosmos section, which explores the science and philosophy of studying the universe, and it does so with just such a wonderful style with this merger of art, culture, science, and discovery. You can join as a digital-only member or in print to receive 6 beautifully illustrated, award-winning collectible editions, which are a staple of any home scientist's library. So join me in reading Nautilus by heading to joinnautilus.com/Dr. Becky, and you'll get 15% off your membership. So thanks again to Nautilus for sponsoring this video, and now let's dive into all the details of what are featureless disk galaxies and why we even care about them. So first of all, just classifying the shapes of galaxies is incredibly useful to us scientifically. It tells us about what a galaxy has been through in its lifetime. It's like a fossil record. Has it been disturbed or become unstable or even merged with another galaxy to become just a giant blob of a spheroid shape? Now, thanks to the fact that light travels at a set speed, so it takes time to get to us, as we look at more distant galaxies, we actually see them as they were when the universe was much younger. We're sort of looking back in time with distance, which means we then get to observe how the shapes of galaxies change with time and learn how the universe has evolved to look like it does today. And a big question people are trying to answer is, when did everything cool and settle down after the chaos of the universe's younger years for nice big ordered rotating galaxies in thin disk shapes start to appear? And thanks to JWST, very recently people have been excited to find galaxies with these big spiral structures, maybe even barred spiral galaxies as well, out to much greater distances and earlier times than has ever been seen before. And that time was way earlier than any of these big cosmological simulations that try and simulate, the entire universe evolving, had ever predicted that these disk galaxies, these very settled, calm galaxies, would start to appear. Although there are some studies that have suggested that that's just due to the fact that to have a large, universe-sized simulation, you just don't have enough simulated particles per galaxy in that simulation to accurately track the physics of what's causing the changes of shape in a galaxy. The only simulation, at least that I know of, that has actually been able to make disk galaxies at really early times in the universe found that they were actually featureless disk galaxies. So a very flat, thin, rotating galaxy that doesn't have any structures in it. So no spiral arms, no bar structure, no clumps, or even a bulge in the center. Just stars distributed really evenly and smoothly in that flat disk. Now, usually when we see a galaxy that is very sort of smoothly distributed with its stars, it's in a big spheroid galaxy that forms after two galaxies merge together. And in that case, you've got something with completely random motion. The stars are still orbiting the center, but there's no pattern to it, kind of like a beehive with just chaos reigning. But in the very nearby universe, we have seen disk galaxies that are still rotating with a nice pattern, but that have this smooth distribution of stars. For that to have happened, those galaxies have to have been completely left alone their entire lives, just not disturbed at all. Otherwise, if you have any sort of instability that ripples through the galaxy, you're going to end up with spiral structure or a barred structure, or even just one of those bulges in the center. And so the question is, if we see these featureless disk galaxies in the nearby universe, do we also see them in the very early distant universe as well? Are they the starting point for all of the spiral galaxies that we see around us today? Or are they some end point of a different part of evolution of the galaxies can take? What time in that sort of like universe's history timeline do these featureless disk galaxies start appearing? And just a quick aside, because I know some of you at home will be like, but don't you study supermassive black holes and how they grow? You don't study disk galaxies. But I specifically study how supermassive black holes grow in galaxies that have never had mergers, which are the isolated disk galaxies. So if you get to understand how they grow and perhaps where they even start from, you have to understand the disk galaxies and where the disk galaxies came from in the beginning. But the problem is, without those features like spirals or bars that stand out so much, featureless disks become increasingly difficult to spot the more distant you go, making it quite difficult to answer this question. Which brings me to how we actually found these featureless disks in JWST data thanks to the citizen science project Galaxy Zoo. So first of all the data that we used were images from the Cosmic Evolution Early Release Science Survey, SEERS, a survey of just a small patch of the sky that was done with JWST in order to detect as many distant galaxies as possible. And in the first initial data release, there were 7,679 individual galaxies identified in the images. And if you want to find a certain type of galaxy in all of that data, then you classify them yourself, right? So yes, I could have sat down and looked at all 7,679 of those images myself and picked out which of them were featureless disks. I could have, cleared my work calendar for let's say a week and just made that my 9 to 5, and I would have cracked through them all eventually. The problem is, individual humans make mistakes. And so when you're looking through data like this, it's always better to get multiple people to look at every image so that you get some statistics. And the more people you get to look at each image, the better. And so a lot of the times you see science teams doing this, where they do like expert visual classifications of the images they have. But usually that's only a handful of people, which is doable for a sample size like this at around about 7,000. But that's not scalable when you start to get more data. This initial release from SEERS was just the first little batch. So what do you do when it becomes tens of thousands, hundreds of thousands, into the millions or even billions of galaxies with some surveys? Well, thankfully, this is already a solved problem thanks to the combined efforts of citizen science projects with machine learning algorithms, aka AI. So the Galaxy Zoo project has been running for nearly 15 years now, and it asks members of the public to classify images of galaxies so that we end up with at least 40 people having classified each galaxy. It's those classifications that are then used to train a computer algorithm how to do this, aka AI. And while yes, AI has massively advanced this field, it can't do it alone, it still needs a huge number of already classified data to be able to learn from those classifications so that you can get reliable results out of the predictions that the machine learning algorithm makes. So as a team, we, like the Galaxy Zoo team, have done this most recently with images from DESI and also Euclid, two big surveys that I've talked about before on this channel. And we cannot continue to do this science if we don't have your help. We have images on the Galaxy Zoo site all of the time, so if you ever find yourself with just a few spare minutes, every classification is useful and gets put towards doing real science, like my paper that's been published this month. And in this case, it was running Galaxy Zoo with JWST data. So back in June to November 2023, the images from Sears were shown to volunteers on the Galaxy Zoo website, resulting in 311,000 classifications from 6,957 people. One person even did 6,945 classifications. So they almost looked at all 7,679 galaxies. So if you ever went on the Galaxy Zoo website during that time period and did just one classification, a big thank you from me on behalf of the whole Galaxy Zoo team for making this science possible. So once all those classifications are then aggregated together in your big data table, what you get out for each galaxy is a fraction of how many people classified it in a certain way. So for example, the first question that was asked, maybe 20% of people said a galaxy was smooth, whereas 80% of people said it was featured. Now, even though that first question that we ask in Galaxy Zoo specifically asks, does it have features or a disk? We've shown in previous iterations of Galaxy Zoo that the volunteers are swayed more by the presence of features than if something looks like a flat disk galaxy. To be fair, this is really hard to pick out by eye, even for an expert, but as a general rule of thumb, like a disk galaxy will have a defined edge, whereas a, spheroid elliptical smooth galaxy will sort of just like fade out the further out from the center that you get. But what that means is that we know that the majority of Galaxy Zoo volunteers are going to classify a featureless disk as a smooth galaxy in the smooth category, which then ends up being a mix of the featureless disks that we're interested in this case, and then the spheroid galaxies, which were formed after a collision of two galaxies that are very different from a featureless disk. So how do you actually then pick out the featureless disks from that mix? I think you've got two options. The first one being, once you've narrowed it down to all the things that people agreed on were smooth, or at least the majority said were smooth, you then eyeball all of those galaxies yourself again, which isn't really scalable the more data you end up with. Or your second option is to fit a model for how the light behaves in the image of each galaxy. Does it cut off like you would expect a disk to do, or does it fade like a spheroid? This is what's known as fitting a Sirsic index. Now, what was fun for us in this research paper was actually that another team of experts had already done both of those things. They'd visually classified all 7,679 galaxies and gone through and classified, are they a disk or are they a spheroid? And they'd also fit models to those images to get, what was the light doing? How was the light behaving? And did that suggest that it was a disk or was it a spheroid? So this was a paper by Ferreira and collaborators from 2023. And so taking their classifications, we could then plot the fraction of Galaxy Zoo volunteers that said a galaxy was featured against the fraction of experts that said that the galaxy was a disk. So every black cross is a galaxy here. And so what we're interested in is the ones that fall in this top left corner, not featured, but classed by experts as a disk. And there are 839 galaxies that fall in that region. Here's an example of 15 of them just to show you what they look like, and you're getting more distant from the top row to the bottom row. And the first thing we had to check was, are they disks? Did the light behave like you expect it to do in a disk galaxy, falling off very quickly? When we look at the distribution of that number, what we call the Sirsic index, a small number being that it falls off quickly, meaning it's a disk, and a bigger number meaning it fades slowly, so it's a spheroid. The distribution is very similar for featureless disks compared to just normal featured disks. So we're pretty sure that these are disks that we're finding. The most distant of these apparently featureless disks that we found was at a redshift factor of 7.35. So that's a factor of how much the light has been stretched by the expansion of the universe. From the amount the light was stretched, you can then say, okay, the light must have been traveling for this long through the expanding universe, and therefore you can work out how distant the galaxy is from us when that light was emitted, and therefore how old the universe was when we're seeing that galaxy. And if you take that redshift factor of 7.35, you work out the light's been traveling for just over 13 billion years to get to us, meaning we're seeing this galaxy as it was when the universe was just 700 million years old. A settled, calm disk galaxy existing after just 700 million years of the universe's lifetime. But as brilliant as JWST is and how far it can see and the faint things that it can pick up, for example, here you can see how many more featured things it picks up at these distances compared to the smaller Hubble Space Telescope, there are still some limitations, right? As you go out to bigger distances, things do get smaller and they look fuzzier in your telescopes because you're hitting that resolution limit. So the next question is whether these truly are featureless disks, or do they just look that way thanks to how far away they are? Because here in this plot, you can see how we identify more of these apparently featureless galaxies among like the smaller and the fainter things. So this was our first clue that there's something up here. But you can do some like fun back of the envelope calculations with this, because you can say, okay, well, we detected like this population of featureless disk galaxies with all of these different sizes nearby to us. So if we assume that's the distribution of sizes that you expect at like all redshifts, and then we like artificially redshift them as if they're getting like a greater distance away from us, so they're getting smaller, would you actually be able to detect them with JWST? And when we do that, we find that yes, we should be able to. The dashed line is kind of like the limit here, and the grey region is like the region that all of these population of galaxies fall as we artificially redshift them from the left-hand side of the plot to the right-hand side. A back of the envelope calculation is pretty simple though. It just takes into account size. It doesn't take into account the fact that things get fainter as you go to greater distances. And the fact that earlier in the universe they're less massive, so they're fainter again. There's lots of different effects at play, which is very difficult to model, and you need like a full simulation to do this. So we actually used the work of Liang and collaborators from 2024 who looked at this for bar features in galaxies and looked at how many bars that existed at various distances were actually classified as having bars. And they found the effectiveness dropped from 100% of bars identified in the nearby universe to only 55% of bars identified by a redshift factor of 3, or about 11.5 billion light years away. So from looking at that work, we ended up concluding that probably at least half of our apparently featureless disk galaxies that we've identified probably in reality actually do have some features. But that still puts the fraction of disks without features at around about a third. So what does this mean for the evolution of the universe? Why don't these galaxies have features? Like I said earlier, for a galaxy to have features like spiral arms or bars or a bulge or a clump and still be a disk, there must be nothing to disturb it. Whether that's like an external influence, like a merger, an interaction, or a flyby of another galaxy, or whether it's internal to a galaxy, an instability that can send like a density wave through that galaxy and form a spiral, like what we talked about in the video that I made about spiral galaxies a few weeks ago. Or another school of thought is that a galaxy will stay featureless while dark matter dominates over normal matter. There have been papers from Fuji and collaborators and Bland Hawthorne and collaborators that have shown in their individual simulations of galaxies, this is the most important parameter for determining if and when a bar structure will form in a galaxy. Now, from observations, we know that in our vicinity, around the sun, in the Milky Way, that normal matter does dominate over dark matter. And we know that normal matter dominates over dark matter in disks at least for the past 11 billion years. But what about before that? And specifically, what about in a sample of featureless disks? So that is going to be some future work for us testing that hypothesis, because if that's true, then all disk galaxies should start out this way, being completely featureless. And as soon as you hit that threshold of normal matter dominating over dark matter, that's when you finally start forming all of these features, these beautiful spirals and bars and bulges and clumps that we see in the nearby universe. And of course, this result has also kind of like laid down the gauntlet for all of my colleagues that, write code to run these big simulations of how the universe evolves and track how galaxies form. They need to figure out what's missing from those simulations currently that's stopping disk galaxies from forming really early in the universe's lifetime, and specifically work out how you can get a featureless disk galaxy forming after only 700 million years. That'll do. Well, that was fun. It was weird kind of talking about my own research, because, your own research you kind of can't get space enough from it to know, space, you can't get enough space from it to know like what is stuff you sometimes need to explain and what is something that not everybody knows. So make sure you put those questions if I missed something down in the comments, and I'll try and cover them, because maybe I've assumed something that I've like, oh yeah, everyone knows that, because I've known it for so long in my own research, right? But I'm rambling, aren't I? Today, what little throat bit then, a little bit of water. Is the audio actually going? Yes. Sorry, the cable was plugged in for the charging and I couldn't actually see the audio response going and I panicked. Survey. Oh, the S doesn't stand for survey. Amazing. Never the case in astronomy. Oh, the S always stands for survey, and then you're saying like the Sears survey, and it sounds ridiculous. It's like saying naan bread, or chai tea. You're just repeating yourself.